Standing waves. In this lesson, we're talking about wave reflection, interference, standing waves, nodes and antinodes, as well as scientific and musical names. Fixed end reflection. A wave pulse traveling through a medium, for example a string, will reflect when it hits a fixed end. And we can see that right here. So there's our fixed end right there. Fixed end. This reflection will be an inversion of the incoming wave. So you can see how we're up when we're going to the right, and then we're going to be down after we hit the fixed end, and we're going back to the left. Now this is going to be important later on. Interference. Waves can interfere with each other either constructively or destructively. So we have here +1 and +1, so 2 crests, and what that equals is a +2. Now destructive interference is when you're going to have a +1 coming in contact with a -1, and what you get is a 0. You get complete destruction of the waves, and that's called destructive interference. Standing waves, a special case of interference. When waves of equal amplitude and shape traveling in opposite directions meet, it's possible for them to form standing waves. Due to constructive and destructive interference, the wave has the appearance of standing still. And you can see the thing we were talking about earlier about the fixed end, that's going to be shown here and here. So when we do our wave, what happens is that it starts up and then it reflects downwards. So when this wave hits this side, it's up, and when it reflects, it's going to be down. And if we keep doing that over and over and over again, what we see is this standing wave pattern, assuming we keep our wave frequency and amplitude the same. Nodes and antinodes. The portions of the wave which remain still are called the nodes. So the nodes are going to be the blue dots, shown here, here, and here. The nodes are spaced half a wavelength from each other, and therefore the distance between 3 nodes is 1 wavelength. So you can see 1 node, 2 nodes, 3 nodes, and we get 1 wavelength as a result. Areas which contain our supertroughs and supercrests are called antinodes, and that's shown here, here, and here. Check your understanding. The distance between 2 successive nodes in a vibrating string is 10 centimeters. The frequency of the source is 30 Hz. What is the speed of the wave in centimeters per second? So if you have 2 nodes, so that would be something like this. And what that is going to equal to is half a wavelength. Therefore, 1 wavelength is going to equal to half a wavelength times 2, which is 10 centimeters, times 2, which is 20 centimeters. The frequency we're told is 30 Hz. And we are asked for the speed in centimeters per second. So remember the universal wave equation? V equals F lambda. F is 30, lambda is 20. So we get 600 centimeters per second. Distance between the second and fifth nodes in a standing wave is 59 centimeters. What is the wavelength of the waves in centimeters? What is the speed of the wave if the source has a frequency of 25 Hz in centimeters per second? So first up, let's draw what this is going to look like. So we're just going to draw a wave in here. And we're going to say that's the first, that's the second, third, fourth, and fifth node. So it says the distance between the second, so that's the second, and the fifth node, so this distance right here, is 59 centimeters. Now how many wavelengths is this? Well, 1 wavelength, half a wavelength. So we could say that 1.5 lambda equals 59 centimeters. Now if we divide both sides by 1.5, we can find that 1 lambda equals to 39.3 centimeters. So A, the first question is, what is the wavelength of the wave in centimeters? To 2 sig digs, it's 39 centimeters. So that's A. Now B says, what is the speed of the wave? So V, if the frequency is 25 Hertz. So V is going to equal to F lambda, 25 times 39.3 equals to 983 centimeters per second. Now we need 2 sig digs in our answer, so our final answer is going to be 980 centimeters per second. Standing waves, scientific and musical names. So we have a scientific name for our different waveforms. So you can see our waveforms on the right-hand side here. So we can have a first harmonic, second harmonic, third harmonic. That's the scientific name. Now there's a musical name that goes along with it. So the first harmonic is going to be called the fundamental, the second harmonic is called the first overtone, and the third harmonic is called the second overtone. And you can see what they look like with the pictures on the right-hand side. What I'd like you to do is I'd like you to complete this chart, given the information on the right-hand side with these images here. So what I'd like you to do again, complete the chart with the number of nodes, antinodes, and loops in each of these examples. And there's our answers there. So if you didn't get the answers, have a look back in the note, find out where you went wrong, and correct it. And that concludes our lesson on standing waves.